pictures that I took here, mostly here in Formula Student Japan in 2016 and 2015. So number one, look at this. If that suspension is going to break, where do you think it's going to break? Right there. And one solution to avoid that is to have simply the linkage of the suspension going through the center of the road and on the outboard. That's simple. You need to have the linkage going through the center of the outboard road end. Let me give you another example in the next slide. Here you have a decent suspension where you can see the axis of the two linkage of the top wishbone going through the outboard. The pull rod is nearly good. It could have been better if, again, the axis would have been to the top wishbone rod end. Next slide. Let me show you another example. This is a good example where you see definitely the linkage going through the outboard part. Okay, next slide. You had a car actually here in the paddock, which you can see there is a good design there. The lower wishbone pickup point on the upright, the lower wishbone pickup point of the Pushrod, the top of the Pushrod, the center of the rocker, the 2 points that are on the damper, and the 2 points of the droopling of the entry bar must be exactly in the same plane. Otherwise, if you have a rocker like this and a Pushrod like that, you are going to have some bending, and compliance is a bad thing. Let's go to the next slide. This is also a common mistake that I see, unfortunately, too often. You see that the axis of the suspension linkage doesn't go through a node of the chassis. On the right side, you have seen the green axis. If that green axis would have been got there, down, it would have been much better. You are going to have a bending of the bracket. Next slide. And this is also an example which is not so good. On the right side, if the axis of the linkage would have gone from the node of the chassis, it would have been better. Let's look at the next slide with another very bad example here. You have the suspension linkage which is arriving not at the node of the chassis. That is happening most of the time because the people design the chassis first, and then they say, oh, okay, I need to have my pickup point of my suspension there. Too late. Actually, the chassis itself should be one of the last things that you should be designing. The chassis is nothing else than a big bracket which is holding everything together. Next slide. This is a good example. This is a good example where the node, the axis of the linkage goes through the node of the chassis. Although I would say that I would have liked to have a little bit less distance there. The bracket is a little bit too long. The goal is to reduce the compliance causes. You know, if you allow me a simple example, if you have a headache, you take an aspirin, correct? You work on the consequence. But if you have a headache every day, maybe there is a pollution or food, you have an allergy, you're going to work on the cause of the headache. Well, it's the same thing here. You want to avoid compliance, and avoiding compliance, the bad solution is to make the chassis stiffer, and the wishbone with a bigger tube, and the rod end which are 8mm instead of 6mm. The problem with that is that by doing this, you're going to effectively reduce compliance, but you increase the weight. Next slide. This is also the typical mistake here. You are going to have a Pushrod which is arriving nearly in the middle of the lower wishbone, and then of course is going to create a big flexion. And if you want to have the axis of the Pushrod going through the center of the ball joint of the lower wishbone. Next slide. This is decent. and this is decent. In the first case, on the left side, you have the axis of the Pushrod, which is attached, the Pushrod is attached to the lower wishbone. On the right side is directly actuated on the upright, but in any case, you have the axis going through the rod and spherical joint. Next slide. This is a mistake I see unfortunately too often, which is single shear. When you are going to have single shear like this, you are going to have a lot of stress just on one side of the rod end, and that is going to make compliance. Especially when you are on the rear suspension, the toe compliance is one of the most disaster things that you can do for handling in terms of stability. The toe compliance is a factor 5 to any other problem, any other factor in the car. Next one. Yes, that is single shear, and of course you're going to have a better reaction of the forces there. It's going to be much better. By the way, I don't know if you can see it from there, but very good welding. Next slide. This is very bad design, I'm sorry, but the rocker should not be arriving, the bracket which holds the rocker should not be arrived right in the middle of the tube. That is to avoid. You need to decide for kinematic reason when you want to have your rocker. Then you design the chassis and you make sure that the rocker fixation, the attachment of the rocker correspond to a node of the chassis. Next slide. This is another example here where you have the pickup point of the damper or the spring and damper unit, which is also attached in the middle of the tube. And sometimes when I say that, the students said, oh yeah, we know that, but we made the chassis stiffer by using a thicker tube. That's not the right solution, because you're going to make the chassis heavier. F equal ma. The more mass, the more force. The more force, the more deflection. The more deflection, the more you need to make the chassis rigid. And if you make it heavier, then you're going to make more force, and so on. It's going to be always the same issue. Let's go through the next slide, give you a few examples here. I see cars with huge rocker, very, very big. If you divide the dimension of the rocker by 2 on the horizontal side and by 2 on the vertical side, you're going to have the same rocker ratio. Let's take an example. You see the 2 rockers are very big. Let's look at the next slide, and you can see here 2 rockers which are definitely smaller. The one on the left has been machined from CNC, block of aluminium, and the one on the right is simply laser cut sheets of metal and then welded together. I believe that compared to the previous one, it is cheaper, it is lighter, and it is stiffer. So bigger is not better. Try to make it each part light, stiff, simple, and cheap to manufacture. Make it compact. The smaller the car is. By the way, the cheapest way to make a light car is to make it smaller. Okay. Let's go to the next one. Anti-roll bar. That is a classical mistake that unfortunately I see too often. An anti-roll bar is made to work in torsion, not in bending. And you see a huge distance between, on the left side, between the bearing cap and the end of the leverage. And there is something worse also, is the attachment of the bracket in the middle of a tube. So you have many flexibilities. I have seen calculation, a comparison of anti-roll bar stiffness effect at the wheel compared to the calculation, the reality being only 1/3 of the calculation. 1/3, so you lost 70% somewhere, or 2/3. Why? Because of all the compliance. The suspension is not working, the anti-roll bar is not working as you think it should be working. Next slide. Here is another example with a way too big distance there. Same thing. Next one. That is a problem here because, as I told you, the droopling of the anti-roll bar should be in the same plane as the rocker. And you see that the droopling is a little bit on the right side of the Pushrod plane, which is going to create a bending. And you see that the droopling is on the left side of the anti-roll bar leverage, which is going to make the anti-roll bar twisting like this. And you see also that you have a big distance between the anti-roll bar bearing and the edge of the anti-roll bar. And you see also that the bearing cup of the anti-roll bar is in the middle of a tube. Ideally, the bearing cup of the anti-roll bar should correspond to a node of the chassis. Thank you. Next slide. Okay. This is another example here. You have an anti-roll bar which is huge, and this is happening. I want to insist on that. This is happening because people are making the anti-roll bar after the chassis has been designed. So the designer called Complete Car said, oh shoot, I have to put an anti-roll bar now. Where am I going to put this? And there is no place because it was not part of the concept. So if you look at the other side, next slide, okay, you see that you have a big anti-roll bar with, again, a big leverage between the edge and the bearing cap. And then many problems you have. Here, the anti-roll bar has been finished with not a U, but with an L shape. And because you have an L shape, you are going to have compliance. And even worse, if you see the droopling, it arrives in the middle of one of the suspension linkage, which is not very good. Next slide. This is a big anti-roll bar on the left, and this is the big anti-roll bar, a small anti-roll bar on the right. And you know what? You can have the same effect of the anti-roll bar on Newton meter per degree at the wheel, but much smaller anti-roll bar itself. Think small, think compact, think reduced, think light, and easy to manufacture also. Next slide. This is over-constrained, over-complicated chassis. If you look at that, you have at that point 6 tubes and 2 nodes which are very, very close to each other. And if you look on the right side of the picture there, you have an incredibly complicated, I stopped counting there, I think there is 7 tubes arriving at the same, okay. So you are building a Formula Student chassis, not the new version of the Eiffel Tower, okay? So, next slide, please. Yeah, there is no need to make upright heavy. Let me give you an idea. You don't have to copy that, but I've been looking at so many upright for so many years. If you want to target, if you have a 10-inch ring, your upright without the bearing should be in the 325 gram. If you have a 10-inch, it should be in the 400 gram if you do it from fabricated or CNC aluminum. Next slide. This is also one thing. If you have a long, on that car, the Pushrod was about something like this. I didn't measure it, but well, I bet it was something like 600 or 650 millimeter. And what's happening is that the force that you are going to have there is going to bend the Pushrod. So there is a part of the energy coming from the bottom of the tire which is not going into the spring and the damper, but goes in the flexing of the suspension element. The other thing that I see many cars like that. I see car with the spring on the top, okay, very visible. First of all, you have cars who are trying to make a very aerodynamic car, but I guarantee you that this spring on the top there are going to disturb the wing on the rear, number one. And number two, when you think about that, you take a force from the bottom, you go up for the rocker, and then you go back down to activate the anti-roll bar. It's like I want to make an omelette, okay? but the egg is not is in the fridge, but the fridge is at the second floor of my home. I have to go up, take the egg, and then come back to make my omelette. It doesn't make sense to make some long linkage from the bottom back to the anti-roll bar. Next slide, please. That's another thing. I see sometimes extremely huge and unnecessary big and therefore heavy radiator here. Very often I see people doing a fan which is very, very small compared to the surface of the radiator. And so basically you are sucking air through the radiator only for a minimal surface of it. And the other thing is, you see this example here, the air is going to go through the side pod, and then where does it want to go there? Well, it's going to go in the path of lesser resistance. So the air is going to go above and under the radiator, and a minimal part of the radiator is going to be, a minimal part of the radiator is going to be used, and you're going to overheat, and then what you're going to do? Making a bigger radiator, which is going to be heavier and so on. That's not the solution. You need to think efficiency instead of doing it massive. Next slide, please. This is another example from last year. I remember that car very, very specifically. It had a huge radiator, and you see that on the bottom left you have a little circle there, which is the fan, and only a very small part of the fan, a very small part of the surface was used by the radiator. And the other reason is that on the right side you have the side pod, which, guess what, was huge. Why was it huge? Because it had a big radiator, but with absolutely no ducting. Let me give you another example on the next slide. This is a pretty good cooling efficiency. You had a radiator which was very, very small. And it's very efficient, and you can see that the fan now is going to suck the air from the whole thing, and it's definitely more efficient and therefore lighter. And also, the smaller the radiator, the less aerodynamic drag you are going to have. So that's basically it, gentlemen. I want to give you my conclusion here, which is that weight is your enemy, and compliance too. So you need to do everything you can do to avoid the compliance. Make it simple, make it small, make it light, and the way you do that is form, follow, function. The biggest mistake that people do is that they design the car and then they try to think what it's doing. Form, follow, functions. First the function, then the form. Chassis at the end, for example. And voila, that's it. I didn't want to take more time, and I'm going to do my best, and you forgive me for my bad accent, but I'm going to say arigato gozaimasu. Thank you very much. I will be in the paddock tomorrow. If you want me to come and look at your car and give me some critiques and some encouragement and some advice, I will be available, and it will be my pleasure to speak to you. Thank you. Good evening.